All right, sorry about that. When we left off, I was explaining the difference in measurements I got. One of the measurements is different than the other, and I think it's because there's some chatter in this hole. So what do you do? Which measurement do you believe? I feel like I did both measurements correct. I verified both. Um, so this comes down to one of those situations: is do you trust with the pin in it, or do you trust without the pin in it? And the way I would go, first of all, I would say this hole is not good enough. We should be able to do better to where we're not getting this out of round chatter in there. But whatever's going in there, the pin is simulating whatever's going in there. So the center point of the pin is simulating whatever will go in there. And I would either accept or reject based on the pin, and not necessarily without it. But in reality, because I got two different values, kind of on the edge of tolerance for what this part allows, this is something you might discuss before you make a decision. Discuss with an engineer, production, try to get a better finish because you're right on the border. Either way, you check it and move forward that way. But I wouldn't necessarily make that decision on my own. So let's jump back into our video, into our lecture. So just as a review, I'll give you a step-by-step review. So first, zero the dial and the height gauge on a reference surface, such as the surface plate. If you want to involve Joe blocks as well as your registration zero, you can do that as well. So feel free to do that. Move height gauge to pin, sweep the high point. So locate the high point of the pin, adjust your pressure until the indicator reads zero, and again, do not readjust it with your hand at this point. Read the height gauge and subtract the radius of the pin. I like this method. I use it as a lot. That's why I'm showing it to you. I think when you have good holes, it's a very easy way. Sweeping the pin is a lot easier than sweeping the hole, because you avoid all that chatter and you just get the full diameter of the pin. You also, in some situations, not necessarily the way this print is called out, but you don't have to zero on the surface plate. You could zero off of your part if that's how your feature is called. So you could zero on the part somewhere and go down, and then you might need to add the radius of the pin. So remember that when you do the shop math, sometimes it's adding, sometimes it's subtracting. And once again, feel free to do this with the drop gauge. Just to save on time, I'm not gonna set it up on the other camera, but right over here, you can set it up and take your readings. And you might this might be a good place to zero off of a 1 inch. How far did you move from 1 inch? Figure that out, add the radius of your pin, and do the math that way. So I have an example right here of doing that. I'm gonna zero on the top of my Joe block. Picture is not so easy to see, but the top of our Joe block is right here. And we're gonna zero on that. And then we're gonna move the indicator, lower it. Yeah, I think we lowered it in this situation. Oh no, we raised it. We raised it up. Yeah, I should be able to tell from the math. So we zeroed it on a 0.6. We raised it up by 0.0865. And then that becomes a 0.6865. And when you use the radius of the pin that was in there, the 0.3875, oh, maybe that was my error. Okay, so about 5 minutes ago, I should have used my calculator to figure out the radius of the pin. I calculated the radius wrong. I tried to do it in my head. Obviously, I did not do that correctly. So actually, if you do the math correctly, both pins end up at the same. I can tell from how far off my numbers are. So if you plug in 0.189 in my previous calculation, should get around 0.497 or 0.498, just as this one's showing. But I can see now from my whiteboard, I had 0.194 written on, and I should have wrote 0.189 and 310 thousandths. So I apologize for that. When we do the practice exercises, I'll make sure to do it correctly. So when we do our practice exercise video, where I just measure parts and I don't talk about the gauges that much, I'll make sure to do a correct application. So I'm going to leave it in just because, you know what, sometimes people make mistakes like me, and I wasn't paying close enough attention to catch the problem, even though I knew there was something wrong. I couldn't figure it out, but this is showing me right away. But getting back on topic, you know, you can use Joe blocks and drop indicators. You could just zero on this drop indicator granite and lift up and do your math that way. There's a lot of different applications that you could go through. And if you're not sure what you're doing, what I probably should have done is draw it out. Draw your part, draw your hole, draw what the indicator's doing, and whatever fixtures you're zeroing on, and do the math that way. You'll be very easy to see what you add and what you subtract, and in what pieces you add, what pieces you subtract, what order makes the most sense. There's a few more examples. Again, here's an example where I use the scribe. I don't use the indicator. And on this example, on the other side, I flip the part over and do it that way by raising up the clamp and just going off of the bottom surface. I just want to show you a few examples to get you thinking about what's possible. Certainly there's pros and cons to each one. You need to be worried about parallelism between these two surfaces, because this is the datum surface. The surface it's resting on is not a datum, and they may not be parallel. So that's one thing you need to worry about. But you know, this is a possibility if you want to go that route. One more thing, when we talk about gauge pins, you can measure a counterbore depth or any other diameter depth using a gauge pin and a caliper. Essentially, you know, you can drop the pin into the hole, measure the length of the pin, zero on it with your caliper, drop the pin in, and then measure what's left. And that pin is sitting 0.998 deep into the hole because it's sticking up. So that would be like an example on the left side. And if it were, oh wait, if I artificially raise this up, so I'm doing a very artificial example right now, but if I do it this way, now I'm at 1.654 negative. That will tell you how far deep is it. So or how deep is it sitting? Either way, it's just shot math. What you want to watch out for is this picture on the right here. Whichever way you do it, you want to watch out for your pin sitting on a radius. So you can either get a smaller pin or try to move the pin away from the radius if it's possible. But if you're sitting on a radius, it won't give you a good depth. But so just try to, how do I say this? It's easiest if you zero your length on the gauge pin and then check your difference. You can get a direct difference that way. The overall length of these pins is not critical and by the manufacturer, but in reality, these tend to be very parallel. You can run an indicator across these pins and see just a little bit of movement. And counterbore depths, some stepped hole depths, they tend to be open tolerance, which will let you do this very quickly. And sometimes your alternative is to use the depth bar and on your caliper or a depth micrometer. And sometimes that's just not as desirable as dropping a pin in and checking it that way. So you can use a surface plate, when we're talking about surface plate, you could zero right here. Raise it up. Do this again. So you could zero on a surface. Okay. Raise it up. Take a reading. Zoom out 1.004 sticking up from the top, and you can see it's pretty flat. It's not, it's not perfectly flat, but it does make a pretty good quick check for a low tolerance depth, which is again something I've done many times before. All right. I already mentioned this. Gauge balls, not something I have here, but you can use gauge balls in a variety of ways as a hand tool, as a surface plate tool. What's nice about gauge balls is if you have a groove, you can put the balls on the surface plate, drop your part, the groove onto the gauge balls, and then take some measurements with your height gauge. Some other applications, you can use a depth gauge inside of a chamfer, inside of a taper, and you can get some readings. How far does a certain size ball sit inside of a cone, and sometimes a print will be called out that way. There's other applications for gauge bars like this number 4, where you are gonna move it through an internal feature that's not straight. So you can, verify that the size of the hole is consistent for whatever's needed, but the hole may not be straight. It may not be required to be straight. There's a lot of applications for that in 3D printing, additive manufacturing, and even just plastics and rubbers. And then that first one, sometimes you might have to mic over a part that's not necessarily a V block, but actually a part that has a V-shaped groove or some sort of cone, and they'll want to know the distance across from one surface to another. So, but probably the one I use the most is the number 2. Sometimes you're making a part that has a taper, and this can be one way to check that you put the taper at the right size at the right location using a drop indicator on a surface plate. So next up, we've got the feeler gauges. And the reason we're talking about them in surface plate is they have some application in checking flatness on a surface plate. So I have a feeler gauge set here that, you know, most people have this set or one just like it. It's got like 25 different sizes. They're not the most precise gauge, so if you want to get a nice one like this brand here, where they're individual and they are actually a um, precision feeler gauge, you can use those to measure flatness. So what you'll do is you'll take a part, you'll set it on a surface plate and clear out any dust, any debris, or any oil, and you'll start to grab your smallest feeler gauge, which looks like 1/1000 and 5/10 for this set, and you just try to stick it under. You just try to run the feeler gauge under, and wherever you can get it under, you know there's a gap. So this is a 1/1000 and 5/10 feeler gauge, and I'm not getting it under. So this is a pretty flat part, at least on the outside edges. What it might look like, I'll simulate what it might look like. You know, is you'd be able to slide it under fairly easily in some parts, and other parts you wouldn't be able to. But if there was a hump or a concave feature, convex feature, we could try flipping it over and do the same thing. But this part was made with a face mill, and I would expect it to be very flat. So, but it's a pretty good way to check large parts, do a quick sanity check, how flat are you, because we actually don't have a lot of ways to measure flatness. I'm going to go over one more way in a couple minutes here. It'll be the next thing we talk about, but short of a CMM, we don't really have a lot of ways. You know, we're going to have one other way to check it, but this is a good way to do a quick check. And, you know, if you have a problem, you'll see it right away. You keep working your way up the sizes until you get to the biggest one that doesn't fit, and then you call that your flatness error. And as the larger and larger parts get, it may go in certain places and not go in other places, and maybe bigger gaps in some areas than other areas. So just go around and try to find the maximum one that does fit. And then the one that doesn't fit, you know, you call that your maximum error. So when you're using these gauges, I do want to point out there's a few situations where this works great. There's other situations where it doesn't. You know, if you had one corner raised up, yeah, your feeler gauge would go in that one corner and it wouldn't go anywhere else. And you could say, okay, it's flat except for this one spot where there's a flatness error of, say, 3/1000. You could have a wavy situation where maybe there was a bunch of passes with an end mill, created some waves, and you may get your feeler gauge in some of the areas, but you may miss it in the middle sections where you can't get a feeler gauge. So you may only see some of the error. You might miss some of it because of the waviness is in the middle of the part where you can't reach. That goes into the concave in the middle. This bottom left example. So you might not even be able to detect the flatness error because it's convex. Sorry, it's concave in the middle. As you're going around with your feeler gauge, you're not be able to get in any of the edges, but all the error is in the middle where you can't reach it. So you might call something flat that isn't. And then the last one, convex in the middle, you know, you're going to find the error very easily because it'll probably be spinning on the rock. If you give it a spin or if you tap it, that's a great way to check very quickly is something level. If you can rock it, if you can hear it out of balance, then you'll know you've got a flatness error. Next up, I don't have any of these I don't have any of these clamps to show you, but we have talked about fixturing a lot of different ways. And so I wanted to briefly discuss Toolmaker's clamps. They're, they're a really great tool that have, not only do they have the ability to clamp onto a part, but they have pretty much the same error as a 1-2-3 block. It's a little bit higher, 2/10 squareness, 1/10 parallelism. But you know, if you really need to clamp onto something, you can rotate those clamps in any orientation that works for you. And it can be, a lot of times it can be better than trying to build a Joe block stack and V blocks and using these clamps. So keep those in mind. These are a couple of Gibraltar vices. I've used the one on the left at a few different places I've worked. It seems to be very popular. And, you know, I really like them when I need to work on a surface plate and I have something I need to clamp onto that's just a lot easier to work with than 1-2-3 blocks. But our next topic, we're going to go back into flatness here, and we're going to talk about our machinist jacks. And with machinist jacks, you can do what's called a 3-point level and get a flatness check. So what a lot of people, when they start off in metrology, they think they're doing a flatness check when they run the indicator. You know, they set a part on the surface plate, they zero their indicator, and right now they're running it around. They think they're doing a flatness check. And right now what you're actually doing is a parallelism check. It's not a flatness check. They're two different things. The reason it's a parallel check, you've got your datum surface on the surface plate and you have your other surface that your indicator's on. And so your surface plate is taking an average for the datum that it's resting on, and you're measuring how parallel are you to that average. You're not actually getting the flatness of this plane. Same thing if you flip it over and you say, okay, well now I'm going to measure my datum directly. You're not measuring the flatness of this plane either, because now you're measuring parallelism still. It just happens to be you flipped it over. So when we want to measure flatness, we need to use the 3-point jacks. So with the 3-point level technique, we will be able to measure flatness directly. It's the only way we're going to be able to do it, either with a feeler gauge setup or this setup. The only ways we're going to be able to do it on a surface plate. So kind of walk you through it. We're going to mark off a few areas where we're going to jack up the part, put our jacks, and then we're going to mark off those zero locations. We're going to zero them off, and then we're going to, once they're level, we're going to take a reading. So let's do that. So one thing, when you are getting a 3-point jack, these handles here rotate the jacks, you know, higher and lower. So what I recommend you do, take out the handles to get in the way, and put your part on. I can obviously tell, I don't know if you can tell from the front camera, it's way off. So I'm going to eyeball it flatter. Okay, that's probably a little too far. So I'm just eyeballing it. Now I'm going to run my indicator just to make sure I'm starting off close to level on all three. Can't see that, hold on. Probably knocked this around a bunch of times, haven't I? Okay. Let's see, this. What helps you see it? None of this helps you see it. All right. So I'm going to zero my indicator on this jack. Yeah, I'm like 5 thou difference. Here, oh, I can't even get it on. So I probably need to raise this jack. Raise up my indicator. So I'm reading about 0 there. And once you're kind of in the ballpark of like 15, 20 thousandths, like I am now, um, it'll save you some time. So I'm gonna rest my part on the jacks, and I'm gonna mark off the locations where I'm zeroing. I'm gonna use a Sharpie dry erase pen. And I'm marking off right where the jacks are because it makes leveling a lot easier. And now, because I'm working with such a small surface plate, I'm going to verify I can sweep the whole part and you can see everything. I am going to make this a little easier on myself. Rotate this. This is one thing I usually forget. Every time I set up 3-point jacks, I don't really look at my travel. All right, now I can reach everything. So now I'm going to pick a corner to be 0. I'm going to 0 U and go to the other spot. Okay, so I went, you see how much that moved from 0 plus 15? I'm going to grab one of my wrenches and bring this closer to 0. Now, when I do that, it's going to affect the entire shape. So this may not go back to 0 now. Not quite. Let me check the other one. So I'm not quite back at 0. I'm not going to worry about that until I'm a little bit closer on all of these. Having a little bit of trouble I don't normally have. So pretty close on that side, but when I go to this side, 0. Something's a little bit off with this jack. I think I had the nut down here. There's some nuts that tighten everything down. I may have had that engaged too much. So let's redo this. 0. And close to 0. I'm not going to worry about that now until I'm a little bit closer on all of them. Okay. So this process can take a little bit of time, a little bit of patience. All right, now I'm going to try to adjust this one up to 0. See, that's how it should go. I don't know why this one's giving me so much trouble. There we go, it's starting to behave. I think it's a little bit out of balance. So 0 there. I'm gonna make the problem child my actual 0. I'm gonna tighten down this nut. Can't really see it on the camera. That should help it not move. And now I'm gonna slowly, gently, you're 0, you're 0. Now you're the problem child still. Just you got to keep going in this circle, because every time you move one of the jacks, you're affecting the entire orientation of the plane. So you can, like I said, you can chase your tail a little bit, but if you're patient, 0, come on, 0. All right, I've got 3 zeros. So now I've got a 3-point level surface relatively spread apart, and now I can check relative to this perfect plane that I've just created, what is my flatness error? And I'm just going to sweep all the way around, getting a little bit of a error there. That was, maybe a 0.5 thousandths around the hole. And as I sweep outside, it's going to the other direction, and it's going a little high. Oops, fell off. Let's check our zeros again. 0, 0, 0. So I might say out of everything I saw maybe a 0.5 thousandths of wiggle in any direction, which is pretty good. If we remember our feeler gauge check, we saw it was even a 1.5 thousandths shim wouldn't go. And so this error that I measured is a 0.5 thousandths. So that makes sense for why our shim wouldn't go. And it also makes sense because I can tell it was made with a face mill. So that's the 3-point level method. You saw me struggle through it. You saw pretty much everything that could go wrong. But if you start off, leveling it yourself before you put the part on, just try to get them relatively the same location, and then put the part on and do your 0. You can get through it in a methodical way. So here's some pictures of what I did. Zeroing all 3 points, and then sweeping left and right all the way around. Look for the low point, look for the high point, do your flatness error. The picture example, the flatness error is 2 thousandths and 3 tenths. And what I just saw was 0.5 thousandths. So sometimes there's variation between parts, and that's normal. It's normal for manufacturing. That's why we have quality control to verify the variation is within acceptable limits. So we're going to end our discussion with, we've talked about a lot of accessories and a lot of tools in the surface plate family. We're going to end our discussion with what's the best gauge for the job. Personally, I say if you can use Joe blocks, you're going to be increasing your accuracy, minimizing your error. As I said, I try to set up Joe blocks on a surface plate and set my height off of the Joe block, and then make my comparison to the part so that I can say, relative to this 4-inch block, what is my part? Rather than relative to the bottom of the plate, and let this indicator and height gauge travel for 4 inches, because you're introducing some error the more you travel. It's also good when once you do that, you can swing it around your entire part and check the entire part very quickly. If you're going to be using these inside of a slot as like a checking for a slot, for example, our part here does have a slot. If you're going to grab and find what Joe block goes in there, it does a pretty good job of checking the entire slot and making sure there's no pinch points. So we didn't really talk about this before, but if there were a pinch point where it's going, oh, it stops. If you have a go size and a no-go size, you should you'll be able to tell if that slot's in tolerance or not. Your no-go size might be like, okay, it doesn't go in, it doesn't go in. All of a sudden it goes in on the back side. You're like, oh, it's out of tolerance on the back side because my no-go is going in from there. So that can be a really great way. So I like to use Joe blocks as much as I can as a hand tool and as a surface plate tool. Skip to the end. And then everything else is kind of a tie. Whether you want to use, which indicator, which 1, 2, 3 block, Joe block, V blocks, whatever else you want to bring into the equation, as long as you're being repeatable, stable, and try to keep it as simple as you can. That's kind of why I mentioned the toolmaker's clamps, because they can really simplify everything by just using one thing to clamp down instead of building a complicated 1, 2, 3 block fixture that maybe has a support from a machinist jack. Just try to keep things simple, stable, and repeatable. As an example, a plane depth. Let's see what could we do with the gauges we've talked about. We could do the caliper depth bar, least accurate. We could do a pin mic in the caliper depth bar, a little bit better. We could do a depth mic. We could do a drop gauge. We could do a drop gauge off of a pin inside the hole. And we could do a height gauge depth attachment. So we could actually attach a height gauge to this, to the rod here. And they make those that will just, as you go down, your probe goes into the hole, you zero it off of the top, and then you go down and you see how far it went, and you just take a direct reading. So how you choose, as I said, it always depends on tolerance. So look at your gauges. Look at your prints. Look at the gauges you have, the accuracy of the gauge, what the print requires, and make your decision from there. Tighter tolerance requires more accurate gauging. Looser tolerance will let you do quicker, faster, and simpler checks. So, and remember, if you're close to the edge of your tolerance with your simple, quick solution, you may need to set up a better, maybe a height gauge or a drop gauge solution to verify with a better accuracy tool. So I want to thank you for watching this video. It's probably been one of the longer topics because there's a lot to cover and it's not always straightforward. So I appreciate you sticking around for the whole video. I want to ask you to check out the Pragmatic Metrology website for more videos on different gauges and some resources that might help you in your metrology careers. I also want to thank Laney College for providing this part, the Laney Machine Technology Department in Oakland. They provided this part. They have a great program based around manual machining, CNC machining, metrology, CAD modeling, maintenance, pumps, many other courses I can't remember right now. And they also offer certificates you can earn if you take enough courses, say in the metrology section, you can earn an inspector certificate or a machining certificate. They have an associate's degree if you take enough courses. It's a 2-year degree, as well as apprenticeships. So local companies, they want to get apprentices going through. They can take their classes at Laney and do their apprenticeship requirements. So again, they're in Oakland, Northern California Bay Area, the Laney Community College. And once again, I want to thank you guys for watching this video, and please check out the website for more videos. Thank you.